So welcome back to the next part of the previous video. In this video we will derive a possible formula for the physical quantity using the dimensional analysis as we have learned in the previous video. For example 1.5 is given for a time period of a simple pendulum. In this figure a simple pendulum is shown with angle theta, length of the string L, mass of the bob as small m. These are written as length of the pendulum L, mass of a bob, angle theta, acceleration due to gravity g. We know that the formula for simply pendulum is equal to T is equal to under root L over G, but we will derive it using dimensional analysis. First, relation for time period will be of the form T is directly proportional to mass, length, theta and acceleration due to gravity. We will write m, L, theta and d with constants raised to the power a, b, c, d respectively. To convert this relation into equation, a constant is being used where we have to find the values of powers a, b, c and d. Writing the dimensions of both sides, we get enclosing in square brackets capital M of mass, length of L using theta, then LT minus 2 of acceleration due to gravity. Now we will compare the dimensions on both sides, like T is equal to T raised to the power minus 2D. We simply multiply this minus 1 with C minus 2 with D. Similarly M. In order to compare the dimensions of length, there are 3 lengths in this right side of the equation. We will add B, D and C. Next we will equate the powers on both sides and we will get the values of D. When we will get the value of D, we will get B plus D equal to 0. We will put D in order to find this B, and similarly we will get theta as 1. We will put all these values in the equation 1, which we have already named as 1.1. When we will put the values of A, B, theta and D, you will get E is equal to constant L over G raised to the power 1 by 2. The numerical value of constant cannot be determined by dimension analysis, however it can be found by experiments. So in this way you can derive a possible formula using dimensional analysis. Next one is the example 1.6, in which we are given with Stokes law. We are going to find, so this is the Stokes law given to find the dimensions. These are the units of coefficient of viscosity denoted by eta with moving velocity v. 6 pi is a number in no dimension, it is not counted in the dimensional analysis. First we will write in the all the physical quantities in their square closed brackets, then we will separate the coefficient of viscosity, then substituting the values of dimensions of F, R and velocity in right hand side, we will get the dimensions of coefficient of viscosity as kilogram per meter per second, which is required in this numerical problem. This is an important MCQs and short question as well. In the next video we will discuss short questions and numerical problem of this chapter.